Good morning. This lesson is for my Trig-Precalc class, but before I get started, I want to say I hope that everyone's doing all right out there. I'm not sure how I'm going to title this. I'll title it how I title in the title. But what I am sure of are two goals for the day. Our first goal is going to be to investigate the need for logarithms, and our second goal is going to be to define a logarithm. So let's just go ahead and jump into our first goal. We just solved equations that look like 2 to the power x equals 1 over 16, where we rewrite 1 over 16 as, let me find a good marker, we factored it down to, what was that, 2 and 8, and 8 turned into 2 and 4, and then 2 and, or 4 turned into 2 and 2, so this became 1 over 2 to the power 1, 2, 3, 4. And we finally rewrote it as, I have an exponent in the denominator, I want to bring it up, so I changed the sign, 2 to the negative 4. That's a little crowded right here, I'm sorry. We rewrite the equation as 2 to the x equals 2 to the negative 4. And that's not a very good negative, so I'll write a better one that's not very good either. I'll do it like that, okay. And we now can solve for x, right? Because when we have the same bases, that means that the exponents must be equal. So x is equal to negative 4. This is a problem that we can solve. Now, what happens if 2x is equal to a number that 2 is not a multiple of? Say 45. 45 has nothing to do with the number 2. All its factors are in fact odd. So we will not be able to get to a situation where we're able to have the same bases and set the exponents equal. Can't do it in this situation. All right? So we're going to be left with 2x is equal to 45. Now, if we can isolate the x somehow, it's an exponent, not a base number. We can't divide away the 2, right? But if we can isolate the x, we have solved for x. Okay? All right, let's move on. Another situation where we need to isolate the exponent is when we want to find the inverse of an exponential function, like y is equal to 5 to the power x. Remember, when we find the inverse, we switch the x and the y, and we solve for the y. So if I want to find the inverse of this equation, I switch the x and the y, and I'm left with x equals 5 to the power y. Just like before, we need to isolate the exponent. So what do you think logarithms allow? What do you think they allow? Let's think about our first goal for a second. Okay? So think about it. I'm going to clean this up, set up the next part of the first goal, and I'll be back. And the cricket's here. I'll be back. I'm back. So let's go ahead and continue with the first goal, and that's investigate the need for logarithms. So hopefully you figured out why we need a logarithm. Logarithms allow us to rewrite an equation so we can isolate the exponent. That's why we need it. Very important that we can do that, because sometimes the unknown is an exponent. Sometimes we want to find the inverse. So let me continue with the lesson and just repeat what I just said. Using logarithms will allow us to solve 2 to the power x equals 45 and finish finding the inverse of x equals 5 to the power y. Remember, we need to isolate the y to find the inverse. So I'm going to check off our first goal, which is investigate the need for logarithms. And now I'm going to talk about defining a logarithm. Now I'm approaching it a little bit differently here. And the reason is it's a little confusing how the books start off with it. They start off with it as an inverse function, and then magically it turns into an equation that you're solving for the unknown exponent. And so I figure that maybe instead of like starting in one direction and then quickly moving to another direction, maybe we talk about what logarithms can do, and then we see how it's used in either case. And so hopefully that develops a better understanding of the reason or the need for a logarithm and how to use it and when to use it, and maybe we'll understand a little bit better. So this is my attempt at creating my own definition for a logarithm. Logarithm is the following rule. A equals b to the power c is interchangeable with c, and I have the translation here. C equals to log base b of a. So C equals log base B of A. That's our base number, that's our of number. Base number and of number. Let's write that down. We got crickets, we got birds, we got drums. I'm having a really hard time focusing here. Squirrel. Alright, that's our base number, that's our of number. So I want to talk about a few conditions here. That cricket's really going for it today. We have to accept that the value of B can equal 1 and B has to be greater than 0. That's something I am going to explain why here in a sec. If B is equal to 1, then any power of 1 to any power has to equal 1, right? So if B equals 1, then A equals 1. There's nothing interesting here, not interesting at all. So that's why B can't equal 1. Nothing happens. Nothing happens. All right, now B is less than 0, which means B is negative, and C, for example, is 1/2. We are going to square root a negative number. An exponent of 1/2 is a square root, and we have problems when we square root a negative number. So that's an issue. We can't have it. We can't have that be negative, right? Now remember, B has to be larger than 0, because if B is equal to 0 and C is equal to 0, we're in big trouble. This is a big uh-oh. I'm just going to say uh-oh. Above my pay grade. And number 4, since B is greater than 0, which is a fancy way to say B is positive, since B is positive, that implies that A itself must be positive. Right? Any positive number multiplied by itself, any number of times, or rooted, or square rooted, or nth rooted, has to be a positive number. So A has to be a positive number as a result of B being a positive number. All right, and number 5, the exponent can be any number. There's no restrictions on it. All right. So remember, we just talked about what happens when an exponent is negative. What happens when the C is less than 0 or is negative? What happens to the value of B, right? So that's something we need to think about. Now let's go back to our 2 examples here, and let's just work our way through our logarithmic rule and see if we can solve it. Now, do we know what the answer means? No, but we solved it. And we'll get more into that later on. But again, the point of this lesson is I really want us to understand and stress we can isolate an exponent. That's what it allows us to do. I can't stress that enough. All right, so let's solve 2x equals to 45. Well, 2 is the base number, that's my B, x is my exponent, and 45 is my of number. So what that's going to turn into is, remember, it isolates exponents, so x is equal to log base 2 of 45. So we solved it. Now, what does that mean? We'll talk about that later. I just need you to know how to rewrite exponentials in logarithm form. All right, and let's finish finding the inverse. X equals 5 to the power y is interchangeable as an exponential function. I now isolate my exponent, and that's equal to log base 5 of x. All right, and this would actually be the inverse of our original function, which was y equals 5 to the power x. So again, I just wanted to introduce the last ingredient of this school year, which is going to be the logarithmic concept of isolating exponents. And now we know how to rewrite them. Now we can go down the avenue of using them for inverse functions or using them to solve equations, and not starting off with the inverse and then bouncing to equations. To me, it just makes a better storyline. And if I understand it, hopefully you understand it a little bit better as well. So I'm going to go ahead and end this here. Again, I hope everyone's doing all right out there. The cricket, I think, is doing fine. Have a great day, everybody. Bye-bye.